Okay, so up on top, we're renaming those. So what we have to do is figure out what we're multiplying by. So for number 1 here, what do we have to multiply the 4 by to make 32? 4 multiplied by 8. So then the 3 has to also be multiplied by 8 to make 24. So 24 32nds. And the second one, what do you multiply the 6 by to turn it into a 30? 6 times 5. So I have to do the 1 times 5 to make 5 30ths. And for the 2/5, what do we multiply the 5 by to turn it into 15? 3. So we multiply 2 by 3 to get 6. So now again, 24 32nds is equivalent to 3/4. So the same value, they just look different. Same here, 5 30ths is the same amount as 1/6. They just look different. Same with 6/15. Same value or same amount as 2/5. They just appear different. We'll look later today, we'll look at why do we need to rename some of those, actually over the next couple of days. Anyway, number 4, we're converting those to mixed numbers. Remember, the easiest way to convert to a mixed number is to do a division with a remainder. How many times does 4 go into 27? 6 times. 6 times 4 is 24, so there's 3 left over. So what that's telling us is that this is 6 whole objects with 3 pieces, or 3 of those fourths left over. So 6 3/4. Now we don't always have to write it out like this. A lot of times we can do it in our heads, like number 5. 5 goes into 23 how many times? 4 with how many left over? So 4 3/5. 7 1/3. 3 goes into 7 how many times? Sorry, 7/3. 3 goes into 7 how many times? Twice with how many left over? 1/3. Perfect. Notice in all of these, the denominator doesn't change. It stays fourths. This stays fifths, and this stays thirds. The denominator doesn't change. All we're doing is taking some of these pieces up here and putting them together to make whole objects. Now 7 through 9, we're going the opposite direction. We want to take these mixed numbers and convert them back into improper fractions. So we want to take this whole number and break it into pieces. How do we know how many pieces? The denominator tells us. So those 3 whole objects get broken to 8 pieces each. So we do 3 times 8, which is 24. Then we add the 5 onto it because there's already 5 pieces there. That's 29 eighths. So 3 5/8 is equivalent, or the same value as 29 eighths. 5 1/3, we do 5 times 3 is 15, plus 1 is 16 thirds. 7 3/4 will become 31/4. Good. 7 times 4 is 28, plus 3 is 31/4. So we can convert back and forth. Now the skill we probably use most often is this next one, reducing. We have 32 over 36. What can both of those be divided by? 4 works. What's 32 divided by 4? 8, and 36 divided by 4? 9. 8/9 is as small as we can go. 15 and 21 can both be divided by 3. 15 divided by 3 is 5. 21 divided by 3? 7. And both of those are prime, so can't divide by anything else. 30 and 75 can both be divided by 5 works. What's 30 divided by 5? 6. 75 divided by 5? 15. Now we see that we can still divide both of those by 3. 6 divided by 3? 2. 15 divided by 3? Careful. 5. So we had to divide twice there to reduce that one. If we had seen it, we could have divided by 15 right away. But as we see, we don't have to find that largest number. Any number that divides both of them will do, and we just keep going until we can't do it anymore. We'll get us to the simplified fraction. 24 and 40 can both divide by, careful, no 0 on the 24. 4 will work. 24 divided by 4, 6, and 40 divided by 4 is 10. Both of those will still divide by 2. 6 divided by 2 is 3, and 10 divided by 2 is 5. So 3/5. So again, you see, if you'd seen it, you could divide by 8 right away, but you don't have to find that largest common factor. You can just keep going. Now, another way we could do this, we talked about factoring a week or so ago. Factoring is actually an extremely powerful tool, like a 32 over 36. If I factor 32, 32 actually factors into 2 times 2 times 2 times 2 times 2. 5 2's multiplied together to make 32. 36 factors into 2 times 2 times 3 times 3. When I reduce these, we divided by 4 up here to reduce them before, but we could also just look at it piece by piece by eliminating common factors. If I divided both the top and bottom by 2, that just cancels out a 2, doesn't it? I can divide by another 2 because there's another 2 in common. Well, there's nothing else in common, so I can't reduce anything more, but I just multiply them back together. What's 2 times 2 times 2? 8, and 3 times 3? 9. So there's my reduction, 8/9. Like over here, 30 over 75. 30 reduces to 2 times 3 times 5. 75 is 3 times 5 times 5. Any common factors I can cancel out. A 3 and a 5. What's left on top is just the 2, and on bottom is just the 5, 2/5. I've reduced that fraction. The same with my 24/40. 24 factors into 2 times 2 times 2 times 3. 40 factors into 2 times 2 times 2 times 5. What cancels out? A 2, and another 2, yes. So we're left with just 3 over 5, which is what we had. Why is this important? Well, it's not at this point if we're working with just numbers, because most of you can look at them and you can see things that can be divided out. So just dividing them out is probably easier when you're working with just numbers. However, at some point, we're going to throw in variables. So we might ask you to reduce something like this. 12x squared y over 18xy to the third. Well, if I go to factor something like that, 12 factors into 2 times 2 times 3. X squared is just x times x. And then we have the y. 18, if I did the factors of 3, is 2 times 3 times 3. Then we have the x. Then y to the third is 3y's multiplied together. Well, now factoring this is quite simple. I can cancel out a 2. I can cancel out a 3. I can cancel out an x. I can cancel out a y. Then what I'm left with on top is a 2 and an x. On bottom, I have 3 and then y and y, so that's 3y squared. Now I've reduced a fraction. I'm going to have you try one in your notes here quick. We're going to have you do 30 do x squared y to the third over 45 xy. We'll give you a couple minutes and then we'll talk about that one. So 30 factors into what? 2 times 3 times 5. Then, of course, x squared is just 2 x's. And then, I'm sure what you guys ask a lot of times after this class, why? And then 45 factors into, yeah, I'm going to put them 3 times 3 times 5, yep. And then just the x and the y. What cancels? We can cancel a 3, we can cancel a 5, an x and a y. So on top, I've got just the 2 and then y, so 2, oops, there's an x up there yet too, isn't there? 2x y squared, and on bottom I just have the 3. Any questions on those? Okay. We will come back and spend more time working with fractions with variables in them. Just wanted to give you a little bit of a jump start on them. Some people do really struggle when you throw the variables in just because it's not what your mind's used to seeing, and it kind of, a little bit of a sense of panic sets in at times. What does that mean, 5 over 5? It's equal to 1. Remember, our definition is the bottom number tells us how many pieces it takes to make a whole object. The top is how many pieces we have. We have 5 pieces, and it takes 5 of them to make a whole object. So we have exactly one whole object. What's that equal? 1. It doesn't matter whether the numbers are there or not. If the top and the bottom, if the numerator and denominator of a fraction are the same, it equals 1. It could be something like 72 x to the 5th, y to the 8th, z to the 27th over 72 x to the 5th, y to the 8th, z to the 27th. It's going to equal 1 because the numerator and denominator are the same. What if the numerator of that fraction is 0? What does that mean? It is equal to 0. This is saying it takes 8 pieces to make a whole object, but we don't have any pieces. We've got nothing. That's 0. 0 stands for nothing. The trickier one is this one, 8 over 0. The 0 is saying it takes no pieces to make a whole object. Well, how can you make a whole object out of no pieces? Well, the answer is you can't. This is not possible, or often referred to as undefined. We've mentioned a couple of times that a fraction and a division problem are kind of interchangeable. You can turn a fraction into a division problem and a division problem into a fraction. If I turn this one into a division problem, 0 over 8 would be 0 divided by 8. My calculator handles that just fine, spits out 0. But if I took this one as 8 over 0 and I put it in my calculator, 8 divided by 0, anybody want to guess? It gives me an error. Division by 0 error. It's saying you can't do this. You cannot divide by 0. Dividing by 0 is actually a very bad thing. Remember, definition of division. We've really seen two different definitions of division. One was that repeated subtraction, right? If I had 15 divided by 5, that meant I was going to subtract 5 till I hit 0, or couldn't subtract 5 anymore. 15 divided by 5 equals 3 because I could subtract 5 3 times. Well, what if I had something like 12 divided by 0? Well, 12 minus 0 is 12. Minus 0 is 12. Minus 0 is 12. How many times can I subtract 0? I can go on forever. It's infinite. And there are some branches of math that do try to define division by 0 as infinity. That sideways 8 is actually the symbol for infinity. But there's issues with that. I mean, if we look at it like that, infinity makes sense. You can divide it an infinite number of times. But the other definition of division is 12 divided by 3, remember, is asking what number times 3 equals 12. Well, we know that 12 divided by 3 equals 4. Well, 4 times 3 does equal 12. Eight divided by 0 equals something would have to imply that blank times 0 equals 8. If I let something divided by 0 equal infinity, well, does infinity times 0 equal 8? No, it doesn't. Anything times 0 is 0, no matter how big. Well, can I make an infinity that's large enough that it overcomes the 0? Well, possibly, but how do I know that that's going to equal 8? So even defining it as infinity is sloppy because we cannot reverse this process. We can't say that this infinity times 0 equals 8. Unless we started, there is actually a branch of math that tried to do this at one time and say that 8 divided by 0 was infinity sub 8. So that infinity sub 8 times 0 equals, I don't want to confuse you by saying any more about that. It's just trying to overcome all the weaknesses of trying to divide by 0. It's really complex, so we just don't divide by 0. I think I shared with you guys the battleship navigational system. Maybe I did. This was back in the late 80s, early 90s, somewhere in there. When the first satellite navigation was becoming a huge thing for all of our military equipment. And one of the large carrier, I believe it was a carrier actually, not a battleship. They had been using it for about a year and a half and hadn't had any issues. Where they put in the coordinates of where they wanted to go in the system, accessed the satellite, got their current position, and calculated the most efficient path to get to where they wanted to go. Well, for some reason at this particular day, the coordinate they put in happened to exactly line up with one of the coordinates they were at. So when the system did the subtraction, it ended up with a 0 and it divided by a 0. Well, what does that do to a computer? Well, the exact same thing it does to my calculator. It gives it an error and locks it up. Now, most calculators and newer computers are set so you can just clear them out and you're good. Back then, a computer tried to divide by 0, it locked up, and the only way to get around it was to power it down and power it back up again. Well, those large ships like that, the electronic system, the navigational system, takes hours to power down and power back up to reboot. So you had a multi-billion dollar piece of equipment floating dead in the water for hours to reboot the system because they tried to divide by 0. Most programs put a safety in there to keep them from doing that, so you don't end up dividing by 0. At some point, I'll give you guys an extra credit too, by the way, that deals with if you divide by 0, some things you can do. Or some, yeah, I don't want to give it away. Remind me at some point and I'll give you extra credit on that. So anyway, I want you guys to try to reduce a couple more fractions. Reduce that one and this one. Do those two and we'll talk about them in a minute. Okay, let's see how you're doing with these. So the first one we're going to factor. What does 9 factor into? 3 times 3. And then, of course, x squared is x times x and then y. 12 factors into 2 times 2 times 3. Then we have the x and y to the 4th. So 4 y's. What will cancel? A 3, an x, and a y. What's left on top? 3 and x make 3x. On bottom, we have 2, 2, y, which makes 4y to the 3rd. Very good. The second one, what does 35 factor into? 5 times 7. Then we got d to the 8th. And n to the 2nd. 49 factors into, it's kind of a tough one, 7 times 7. Then we got 5 d's and 3 n's. What cancels? A 7, 2 n's will cancel, and 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So on top we've got a 5 and we've got 3 d's. 5d to the 3rd, and on bottom we've got a 7 and an n. Now let's take a look at those results a little closer. The numbers, 9 over 12, reduce just like they would if the variables weren't there. 9 and 12 both divided by 3 give me 3/4. That's part of my answer right there. So the numbers are not affected by the variables being there. So if we could figure out a way of working with the variables, it would make this a lot easier. Well, if I look at just the x's here, I have x squared over x. Remember, we can think of that as x to the 1. Well, first of all, where did x end up in my answer? On top. What power does it have? No power or just a 1, right? So if I look back at what we had over here, looking at the x squared and the x to the 1, what there would indicate that it's going to end up on top in my answer? Okay, yeah, the bigger power is on top, the 2. So that's what indicates it's on top. And then you're right, we subtract. 2 minus 1 is 1. Let's see if that holds for the y. So this is y, and y to the fourth, we can think of that as y to the 1. Where's the bigger power? On bottom. Guess where the y ended up in our answer? On bottom. We have 4 and 1. 4 minus 1 is 3. We end up with y to the third, and it's on bottom. So let's look down here. Same thing, our numbers can be reduced just like the variables aren't there. 35 over 49. Well, we know both of those can be divided by 7. 35 divided by 7 is 5. 49 divided by 7 is 7. That's the numbers we got in our answer. The variables. D to the 8th over D to the 5th. Where's the largest power? On top. So that tells us D is going to end up on top in our answer. We have an 8 and a 5. The difference would be 3. So we ended up with a D to the third on top in our answer. How about N? Is that going to end up on top or bottom? Bottom. Bigger power is on bottom. 3 is bigger than 2. The difference is 1. So we get N to the 1 or just N on bottom. So we can use that shortcut to reduce these fractions. So we might have 24 a to the 5th, b to the 3rd, over 16 a to the 3rd, b to the 9th. So looking at these, I'm going to start out with the numbers, the 24 over 16. What can both of those be divided by? 4 will work. 8 would work too, yes. What's 24 divided by 4? That's 6. What's 16 divided by 4? 4. And you're right, they can still both be divided by 2. 6 divided by 2 is 3. 4 divided by 2? 2. Now, if this were a simple fraction with no variables, 3 over 2 would become 1 and 1/2, wouldn't it? Here it does not. It's going to stay 3 over 2. Why can't we turn that into an improper or into a mixed number, 1 and 1/2? Well, because that 1 and 1/2 indicates that the numerator was bigger than the denominator, so we had to split it up. Here, it isn't just 3 in the numerator, is it? We have A's and B's. Do we know what the value of A and B are? No. So the denominator might actually be bigger than the numerator, even though the number part is smaller. With the variables, the denominator might actually be bigger. So now for A, is A going to end up on top or bottom in my answer? On the top, because A to the 5th is bigger than A to the 3rd. So A goes on top, and what power does it have? 2. 5 minus 3 is 2, so that's A to the 2nd, or A to 2 on top. B is going to go on top or bottom? On bottom, we have B to the 3rd and B to the 9th. B to the 9th is the bigger power. So B goes on bottom, and it'll have a power of 6. 6 minus 3 is, or sorry, 9 minus 3 is 6. So B to the 6th. Now here, we do not know what value A and B have. So we do not know if this is an improper fraction or not. So to make that 1 and 1/2 then with the A and the B would not be correct. We cannot do that. So it must be left like this. Even though the number on top is bigger, it has to stay that way. We might have 42 x to the 7th, y to the 5th, z to the 8th, over 28 x to the 4th, y to the 9th, z to the 9th. So we're going to start out with our 42 and 28. What can both of those be divided by? 7 will work. 42 times 7 is, or 42 divided by 7 is 6. 28 divided by 7 is 4. Are we done? No, both of those can be divided by 2. 6 divided by 2? 3. 4 divided by 2? 2. So my answer, the numerical part, the number part is 3 over 2. Again, we cannot make that a mixed number. It has to stay like that. X is going to go on top with a power of 3. Good. The larger power was on top. And then 7 minus 4 makes 3. Y is going to go on bottom with a power of 4. Good. The larger power was on bottom. 9 minus 5 makes 4. Z goes on bottom with a power of 1 or just Z. 9 minus 8. 9 is the bigger power. 9 minus 8 is 1. So Z to the 1 or just Z. What do you think? Good. I'm going to have you guys try a couple of new notes. So 27 a to the 5th b over 45 a to the 7th b. And 60 m to the 9th n to the 5th p over 24 m to the 8th n to the 8th p to the 8th. Okay, it's our break times. Let's go ahead and take our break, and we'll talk about these at 9:30 when we come back. So, like I said, need a different community. Okay, so for this first one here, 27 over 45. And I do generally write them off to the side just with the numbers, just to make it easier for me to reduce. Both of those can be divided by 9. Gives us 3 over 5. So we got 3 on top, 5 on bottom. How about our variables? Where's the a going to go? Bottom, and it will be a power of 2. Good. A to the 7th was the bigger power. 7 minus 5 is 2. B goes away. Cancels out, right? 1 minus 1 is 0. B to the 0 is nothing. So we just have 3 over 5a squared. The next one over here, we've got 60 over 24. Both 60 and 24 can be divided by 12 will work. What's 60 divided by 12? 5, and 24 divided by 12. 2. So we make that 2 1/2? No. It does have to stay 5 over 2. We never turn them into mixed numbers when they have variables in them. Where does the m go? On top with a power of 1, or it just stays m. M to the 9th was the bigger power. 9 minus 8 is 1, so it's just m. Where does the n go? Bottom with a power of 3. Good. The 8 is the bigger of the 2. 8 minus 5 is 3. P is going to go on bottom with a power of 7. We think of this as p to the 1. 8 is bigger than 1, so it goes on bottom. 8 minus 1 is 7. What do you think? Doable? Okay. So, what if I tell you that I need a specific denominator? Like we have something like, come on now, 3x squared over 5y. And I tell you that we need the denominator of 20xy. Let's do this parallel to something like this. If I have 3/7 and I want to make it something out of 42. If I don't know what to multiply 7 by to turn it into 42, I can just reverse this. I can do 42 divided by 7, which is 6. That tells me I'm multiplying by 6 on top and bottom, right? I can do the exact same thing over here. If I'm not sure what to multiply 5y by to turn it into 20xy, I take my 20xy and I divide by 5y. What is 20 divided by 5? 4x divided by nothing is x, and y cancels out. Right? So it's just 4x. So it's 5y times 4x. I'm going to double check to make sure this works. 5 times 4 is 20. Y times x is just yx, or xy if you put it alphabetically. So I'm going to multiply the numerator by 4x. 3 times 4 is 12. X squared times x. X to the third. Remember, think of that as x to the 1. When we're multiplying exponents with the same base, we add the powers. So we get 12x to the third over 20xy. Let's do a couple more of those. Let's say that we have 7ab over 10, and we need to have 50 a squared b to the fourth. Now again, you might get to where you can look at this and you can tell what you're going to have to multiply by here, but until you get to that point, let's just do 50 a squared b to the fourth divided by 10. 50 divided by 10 is 5. Yep. What happens to the a squared b to the fourth? Stays the same. Absolutely nothing happens to it because there's no variables to divide by down here. So this is times 5 a squared b to the fourth. Now again, we're going to double check. 10 times 5 is 50. And then just the a squared b to the fourth is nothing to combine with. So that does give us the 50 a squared b to the fourth. Now we're going to multiply the top. Times 5 a squared b to the fourth. What is 7 times 5? 35. What's a times a squared? A to the third, and b times b to the fourth. B to the fifth. So 35 a to the third, b to the fifth over 50 a squared b to the fourth is equivalent to 7ab over 10. We might have let's do 25 x squared y to the third over 7z squared. And we want this to be 21 xz to the third. So again, we have to figure out what we're going to divide by down here. So I'm going to do the 21 xz to the third divided by 7z squared. So 21 divided by 7? 3. X divided by nothing is X, and then Z to the third divided by Z squared is just Z to the 1 or Z. Now first, I'm going to stop. Any questions as to where this came from? I just took the new denominator divided by the old denominator. So I'm multiplying by 3xz on the bottom and on the top. So on top, 25x squared y to the third times 3xz. What's 25 times 3? 75. X squared times x. X to the third. What happens with the y? Stays the same, so just y to the third and a z. So 75 x to the third y to the third z over 21 x z to the third. Let's have you guys try a couple here. So if we have 12 ac squared over 35b, and I want to turn this into 70 a squared b. And then the second one I want you to try, we're going to do 15 x squared y over 8 z squared, and we want to turn that one into 40 x y squared z to the third. So I'm going to give you a couple minutes to try that. Okay, so for the first one here, do 70a squared b divided by 35b. We divide that out, what do we get? 70 divided by 35 is 2a squared divided by nothing. A squared and b divided by b cancels out. Very good. So we're multiplying by 2a squared. So on top, if we multiply by 2a squared, 12 times 2 is 24. We get a to the third and c squared. Nothing changes the c. The next one, we're going to take 40 xy squared z to the third divided by 8z squared. 40 divided by 8, 5. X, just x, right? How about the y? Y squared, nothing divided by z, just z. Z to the third divided by z squared, 3 minus 2 is 1. So z to the 1 or just z. So this is going to be times 5x y squared z. So times 5x y squared z. 15 times 5, 75 x squared times x. X to the third, y will be y times y squared, y to the third, and z stays the same. So 75x to the third, y to the third, z over 40 x y squared z to the third. Now, there are actually a couple other ways we could go about that process. Let's take a look at this one here. And I'm trying to turn that into 7a squared 70a squared b. We've done a lot of talking about factoring. We're going to talk a little bit more. If I factor the 35b, 35 is just 5 times 7, and then of course we've got the b. Over here, 70 is 2 times 5 times 7. A squared is a, and then we've got the b. What we are doing when we do this is we are just putting in missing factors. Both of these have a 5 and a 7 and a b. What's missing is the 2, the a, and another a. That makes 2a squared, which is exactly what we multiplied by up here. Same thing could have been done over here. 8z, or 8z squared is 2 times 2 times 2 times z. 40, 2 times 2 times 2 times 5. X, y squared is y times y. Then z to the third is 3z's. Again, we could look at that and say, well, oops, get back here. We could say both of them have 3 2's. Both of them have 2 z's. What's missing is the 5, the x, a y, and a z. That is 5x y squared z, which is what we ended up multiplying by up here. So I stressed that factoring last week because it is a very powerful tool. In fact, we're going to come up on, in the next couple of classes, looking at how do we find those common denominators. Here I gave you what we were changing it to. I told you we wanted to change it to a 70a squared b, or change it to a 40x y squared z to the third. But if I don't tell you that, how do we figure out what that is? Well, let's take something like 3b over 8a squared and 7c over 6ab. How would I figure out what that common denominator is that I'm going to change those to? Well, we can go back to the factors. 8 factors into 2 times 2 times 2. A squared is a times a. 6 is 2 times 3. A and b. Now, what I was doing up above, one of them was a multiple of the other. So that all I had to do is cross off the common factors, and what was left in the other number was what we needed to multiply by. Here it's going to be a little bit more complicated because there's going to be missing factors on both sides. What do they have in common, first of all? They both have a 2. They both have an a. So the 2 and the a are covered. So now we need to look at what is not in common. This first one has a 2, and another a. So we're going to combine, we're going to multiply the other one by a 2, another 2, and another a. Now those are in common. The second number here has a 3 and a b. So the first one has to be multiplied by a 3 and a b. Now those are in common. Now both numbers have the exact same factors. If I multiply those up, I have 2 times 2 times 3, which is 24. A times a is a squared, and b. To double check to make sure we come up with the same thing, let's check the other one. 2 times 3 is 6, times 2 is 12, times 2 is 24. I have a times a is a squared and b. So 24a squared b. 24a squared b is my least common denominator. And here's the cool part of it. What do I have to multiply the 3a squared by to turn it into that? This piece here, the 3b. What do I have to multiply the 6ab by? That piece there. 2 times 2 is 4a. So this factoring is really the key to what we've done with fractions. We've been doing it since 3rd or 4th grade just by looking at it and trying to figure out what those numbers have to be. But if you're stumped, the factoring will always find the numbers that you have to use to manipulate our fractions. Okay, so just some review of our actions with these powers. We've already had this one, we've already gone over today. X to the 8th divided by x to the 3rd is going to give us x to the 5th. Good. When we are dividing exponents with like bases, both of these have a base of x. We subtract the powers. 8 minus 3 is 5. If we have x to the 7th times x to the 5th, we get x to the 12th. Good. Once again, when we're multiplying exponents with the same base, both of those have bases of x. We add the powers. 7 plus 5 is 12. If I have x to the 4th to the power of 7, I get x to the 28th. Very good. When I have an exponent and I take it to another power, I multiply the powers. 4 times 7 makes 28. Let's explore that one just a little bit more. So when I do this, 5x to the 3rd, y to the 7th, to the power of 4. Just like any other operation, I can take each piece separately. So I start out with 5 to the power of 4. What's that going to give us? Now be careful, it's not 20. Yeah, it's 5 times 5 times 5 times 5, which is 625. Now we can apply our rules for powers. The x to the 3rd to the power of 4 is x to the 12. Good. Y to the 7th to the power of 4? Y to the 28th. Very good. So then here, 4x to the 3rd, y to the 5th, z squared, all to the power of 6. So we start out 4 to the power of 6. What'd you get? 4,096. Good. X to the 3rd to the power of 6. X to the 18th. Good. Y to the 5th to the power of 6. Y to the 30. And z squared to the power of 6. Z to the 12th. Very good. What if we have a fraction to a power? 4/5 to the power of 3. Well, remember, that's just going to be 3 4/5 multiplied together. Well, when we multiply fractions, we can just multiply the numerators, 4 times 4 times 4, and multiply the denominators, 5 times 5 times 5. So it basically turns in 4 to the third over 5 to the third. We've mentioned this before. When we take a fraction to a power, we can just do the numerator to that power and the denominator to that power. So 4 to the third is 64, good. And 5 to the third? 125, good. We might have 2/3 to the power of 5. That's going to be equivalent to having 2 to the power of 5 over 3 to the power of 5. 2 to the 5th is 32. And 3 to the 5th? 243. 32 over 243. I could have something like this. 5x squared over 4y to the third to the 4th power. That's just 5x squared to the 4th power. And 4y to the third to the 4th power. So 5x squared to the 4th power. What's 5 to the 4th power? 625. And then x squared to the 4th? X to the 8th. Perfect. Now we've got 4y to the third to the 4th power. 4 to the 4th power? 256. And y to the third to the 4th power? Y to the 12th. Very good. 3 times 4 makes 12. So you can see, working with the variables does not change the processes. And when we go on to looking at operations with fractions, we're going to also look at operations with fractions with variables in them, because the variables follow the same rules as the numbers. That factoring is a very powerful tool that we'll look at using to help us out. Hopefully at some point you'll get good at just working with it, working with the variables without having to factor, just dealing with our rules of powers. But any questions? Okay. So there is a new quiz. This is on the stuff from last Wednesday. That's going to be due tomorrow, Tuesday, at 11:59 p.m. And there's new homework that will be due Wednesday. Has everybody received their test back yet from a couple weeks ago? Everybody hasn't got it back yet? Okay. Make sure you turn those back in. I've got yours correct. Yep. Make sure you turn that back in for correction so you can get points back. If you have any questions on them, please let me know. I'd be more than happy to sit down and work through the problems you have wrong with you. Or any others for that matter, if you have some that you got the right answer and not necessarily sure how you got them. The quiz will be on my math lab. Yep. So that's all I have for new material for today. So I'll let you guys have some time to either get started or get other things done. And we will see you on Wednesday.